All right, today we're doing something a little different. We're not just going to learn some chemistry, we're going to solve a mystery. We've got an unknown substance, a handful of clues, and our wits. So, yeah, let's dive into this chemical detective story.
So just imagine this for a second. A chemist in a lab gets handed a vial of some totally unknown substance. I mean, where do you even begin? How do you figure out what's actually inside that vial? Well, that's the core question we're going to tackle today.
We're going to treat this problem just like a classic whodunit. We've got our culprit, this mystery compound, and we've got a case file filled with clues. Our job is to piece them all together and reveal its true identity.
Okay, here are the facts of the case. Our unknown is a hydrocarbon, which just means it's only made of carbon and hydrogen. Simple enough. When we burn it, we get a very specific amount of carbon dioxide and water. And finally, we have a rough idea of its size. Its molecular weight is somewhere around 154. These are the only clues we've got. With the case file open, it's time to start the real investigation. We need to turn these raw numbers into some actual, usable evidence that can point us toward our molecular suspect. So let's get to it.
Our main forensic tool here is a technique called combustion analysis. It's a really powerful method where we essentially burn the evidence, our unknown substance, but in a very controlled way. By analyzing what comes out, we can figure out exactly what went in.
So, the crucial idea here, the thing that makes this whole process work, is that atoms don't just disappear in a reaction. That means every single carbon atom from our mystery compound is now trapped inside the carbon dioxide we collected. And likewise, all the hydrogen is now accounted for in the water. Nothing gets lost. So, after doing a little math to figure out how much of that CO2 is actually carbon, we get our first piece of hard evidence. The amount of carbon in our original sample was exactly 0.3833 grams. Okay, one down. We do the same thing for the water. From that 0.479 grams of H2O, we calculate the mass of just the hydrogen, and that gives us our second piece of forensic data, 0.0536 grams. Now we're talking. With the mass of both our elements, we are really getting somewhere.
We have the mass of our elements, which is great, but a chemical formula isn't about mass, it's about the ratio of the atoms. So let's see how this evidence helps us build our case. We're about to create a sort of composite sketch of our molecule. It's called the empirical formula.
The process is a pretty straightforward three-step game plan. First, we convert the mass of each element into moles, which is really just the chemist's way of counting atoms. Then we find the simplest ratio between them. And finally, we just write the formula based on that ratio.
And step 1, complete. After dividing the mass of each element by its molar mass from the periodic table, we find our original sample had 0.0319 moles of carbon atoms and 0.0532 moles of hydrogen atoms.
Now, to find the simplest ratio, we just divide both of those numbers by the smaller one, in this case, the moles of carbon. And when we do that, we find that for every one carbon atom, we have about 1.67 hydrogen atoms.
You can't have 1.67 of an atom, right? We need whole numbers. But if you look closely, 1.67 is really close to 1 2/3, or 5 divided by 3. So if we just multiply our whole ratio by 3, we get a beautiful, clean, whole number ratio. 5 hydrogens for every 3 carbons.
And there it is, our first major breakthrough. The simplest possible formula for our compound is C3H5. This is the empirical formula, and it's our first solid lead in this whole case.
But hold on. Just when we think we're closing in, we hit a plot twist. Our evidence doesn't seem to add up perfectly. There's a puzzling discrepancy we need to investigate.
You see, C3H5 is just the simplest ratio. The actual molecule could be C6H10 or C9H15 or any whole number multiple of our empirical formula. Our job now is to find that multiplier, which we'll just call N.
And to find N, we can use that third clue from our case file, the approximate molecular weight. The logic here is pretty simple. We divide the true molecular weight by the weight of our empirical formula, C3H5, and the result should be a nice, clean, whole number.
So we run the numbers. We take that approximate molecular weight, 154, and we divide it by the weight of our empirical formula. And the answer we get is 3.75. That is definitely not the whole number we were hoping for.
So is this a dead end? This seems like a big problem. You can't have 3.75 units of a formula making up a molecule. So what went wrong? Did we make a mistake somewhere? Or was one of our clues misleading from the very beginning?
Okay, this is where a good detective shines. When evidence conflicts, you don't give up. You reevaluate, you find the most reliable piece of information you have, and you press on. It is time to crack this molecular code once and for all.
And here is the key, the approximate molecular weight. The key word there was approximate. It wasn't an exact number. But our mole ratio, that 1.667 we calculated directly from the combustion products, that is solid. That is our most trustworthy clue. So we're going to stick with that.
So instead of relying on that faulty molecular weight, let's just line up our suspects. Let's just check the hydrogen to carbon ratio for each potential answer. We go down the list. Nope, not that one. Still no. And then, boom, look at option E, C12H20. The ratio of 20 hydrogen to 12 carbon is exactly 1.667. We have a perfect match.
And this brings us to the most important lesson from this entire investigation. Just like the source material says, when you're faced with conflicting data, you have to trust the empirical formula, or really, the mole ratio it came from. It's the most reliable piece of information you have.
And so, the culprit is identified, C12H20. That approximate molecular weight was a bit of a red herring, but the fundamental mole ratio was the key that cracked the whole case. We've identified our molecule. Case closed.